Okay, so at the end of the last video, we were talking about the Doppler effect, how the perceived pitch of a sound will change if the source of that sound is moving. If it's moving towards you, it makes the pitch seem higher. If it's moving away from you, it makes the pitch seem lower. And we ended on this slide where this formula is derived. The change in wavelength is equal to the distance minus the distance of the source, and distance is equal to velocity times time, and then we can substitute in wavelength over the velocity of the sound for time, and that ends up giving us this formula right here that can be used. So the perceived wavelength, the one with the prime here, the way it sounds to us, the way it seems, is the actual wavelength multiplied by 1 minus the velocity of the source divided by the velocity of sound. And typically, we're going to be dealing with sound traveling through air at room temperature. So that's going to be 343 meters per second. Keep in mind, though, that that's not always the case. If we're talking about sound in water, for instance, or if the problem specifically mentions that the temperature being something other than room temperature, that may be different. But for the most part, it is usually going to be 343. So that's the formula for wavelength. What we're usually, though, more concerned with is frequency. So frequency and wavelength are related to each other, and so we can do a little bit of substitution here to come up with this formula here for the excuse me, for the perceived change in frequency, the way sounds seem higher pitched when they're coming at you. And this specifically is for the source moving towards a stationary observer. So like the fire truck moving towards the person. The perceived frequency is the actual frequency divided by 1 minus the velocity of the source over the velocity of sound. And then when the source is moving away from the stationary observer, like the fire truck moving away from the person, then the formula is this. It's the perceived frequency is equal to the actual frequency divided by 1 plus the velocity of the source over velocity of sound. So that when the source of the sound is moving away from you, it sounds lower in pitch. Okay, another way to think of the Doppler effect is, what if the source of the sound is stationary? It's not moving anywhere. What if you are the one that's moving? If you're in a vehicle and you're moving towards the source of the sound, you're going to perceive these waves closer together, because you're not just standing there letting the waves come over you, you're actually running into the waves. So again, if you're moving towards the source of a sound, you're going to perceive it as having a higher frequency. And the formulas for this are similar, but slightly different here. So when it's you that's moving instead of the source of the sound, then the perceived frequency is equal to 1 plus the velocity of the observer divided by the velocity of sound times the actual frequency. And if you're moving away from the source of the sound, the formula here is this. The perceived formula is equal to 1 minus the velocity of the observer divided by the velocity of sound times the actual frequency. So we've got 4 different formulas here, these two and these two, for the Doppler effect. And which one you use depends on, is the source of the sound moving or is the observer moving? And are you moving towards the sound or away from the sound? Leads to these 4 different formulas that we can use. So in this example here, we have a police police car whose siren is emitting a sound at a frequency of 1600 hertz. So if we're standing here and the police car is coming at us, when it's traveling towards us, these sound waves are going to be closer together. They're going to sound higher in pitch, and so the velocity of the source is 25.0 meters per second. And if it's moving away from us, they're going to get stretched apart and it's going to sound lower. And it's going to maintain the same velocity. So we want to know what the perceived velocity will be, or what the perceived frequency will be in these two situations. So if we go back and look at our formulas, it's the first set here where the source is moving, and we want to know what it will be when it's moving towards us and when it's moving away from us. We want to use these two formulas, 12.2a and 12.2b. Okay, so when it's moving towards us, the formula is that the perceived frequency is equal to the actual frequency divided by 1 minus the velocity of the source, so URCE, and the velocity of sound. Okay, so the actual tone being emitted by the siren is 1600 hertz divided by 1 minus the velocity of the source. It's traveling at 25.0 meters per second, and we're going to divide that by the speed of sound in room temperature air, 343 meters per second. And so that equals approximately 1726, or if we look at our significant figures, let's assume that this is exactly 1600. So we're probably going to want to limit this to the 3 significant figures here. So we could say that's 1730 hertz. Now if we compare that to the actual original sound, it's actually 1600, but we're hearing it, the way we hear it, it sounds like 1730. So it sounds like it's a higher pitch frequency. When we look at the car moving away from us, that perceived frequency is going to be equal to the actual frequency divided by 1 plus the velocity of the source divided by the velocity of the sound. Okay, so again, the original source was 1600 hertz. This time we're going to do 1 plus 25.0 over 343. So meters per second and meters per second. And so this is equal to 1491, or approximately 1490 hertz. So 1490 hertz is lower than the original 1600. So as the car moves away from us, it sounds like it's emitting a lower pitch. Okay, so let's look at a slightly more complicated problem where we have a 5000 hertz wave emitted by a stationary source, like the police officer here with his radar gun. It's going to emit a wave with a 500 hertz frequency. It's going to reflect off of a car. So we've got a car over here. It's going to bounce off the car and then come back to the stationary observer. So in the first part of the problem, it's the observer who's stationary, and no, I'm sorry. Let's think of the car as the observer. So the source of the sound is stationary. It is emitted out, and we are moving towards it. We, as the observers in the car, are moving towards it. Once it then bounces off of us, then we become the source, and the radar detector becomes the observer. So the roles get flipped. Originally, the radar gun is the source, and we are the observers. But once that sound wave bounces off of us, we become the source, and the radar detector becomes the observer. The object moving, we, the car, is moving at 3.5 meters per second towards the source. What is the frequency of the wave reflected by the moving object as detected by the detector at rest near the source? Okay, so like I said, first of all, the source in the first part of the problem is stationary, and the observer is moving. So we want to use the formula that the perceived frequency is equal to 1 plus the velocity of the observer over the velocity of sound, multiplied by the original frequency. So that's going to be equal to 1 plus 3.5 meters per second was the velocity of the car, divided by the speed of sound, 343 meters per second, multiplied by the original frequency, that's 5,000 hertz. So that equals 51 hertz. And I won't round that off to significant figures yet, because that's just an intermediate step. I'm not done with this problem yet. So that's the frequency that the wave seems to be by the time it hits the car. Then it bounces off the car, and that's the formula we're going to use here is for when you have a moving source and a stationary observer. So this is going to be 1 minus velocity of the source divided by the velocity of sound. And the way I'm using these tick marks here to identify, we've got the original source of the sound, which has no superscripts here. Then we've got F prime is the sound of the frequency when it hits the car, and then it's going to bounce off with that same F prime. And by the time it gets back to the detector, it's going to be F double prime. Okay, so we're starting with a frequency of 5051, then divided by 1 minus the velocity of the source, which again is 3.5, and the speed of sound is 343, so meters per second and meters per second. And that should give us a final perceived frequency when it bounces back to the detector of 5103 hertz. And if I should probably round that off to 3 significant figures, 5,100 hertz. Okay, so that's one possible way a speed detector could work, based on sound waves and the Doppler effect. This kind of Doppler radar could be used by police to determine, based on the frequency that the sound wave gets bounced back to the detector, they can use that then to solve for your velocity. And it's also used, like I said, in weather forecasts to bounce sound waves off of clouds and other meteorological phenomenon to determine how far away they are and how quickly they're moving.